Alright, chemistry, we're moving on to part 4 of the Thanksgiving assignment answers video, and we're starting on page 9. And this is a problem 27 is a net ionic equation. That is the 9-step problem. Seems kind of long, but remember, if you don't write out each and every step, it really doesn't take that much space. Now this is on the day 29 video right there. And so I'm going to go ahead and just refer you to go to watch that video in the Canvas and watch how you do it. This exact problem is the one demonstrated on that video. Okay, on that same video is the solubility rules. And you see some of those down here. And these are some that are straight off that assignment. These are the ones I don't believe I gave you the answers to. So let's just talk about those. And so you're going to turn to page 10 of your packet. Okay. By the way, if you don't have your packet with you, come in Monday or Tuesday during tutoring and you can pick it up. Okay, or I can give you one. All right. So again, a way to read these is everything over on this side is soluble. Okay, with the exception of the ones that say except. So all these are soluble with anything. Chlorine, bromine, and iodine are soluble with anything except silver, mercury, and lead. So for example, lead iodide is insoluble. It's going to form a solid. Okay, sulfate is soluble with anything except these 5 down here. So barium sulfate is insoluble. Come over to the right side, you have everything over here is insoluble. These are the universal soluble ones. These, and they're the same, you'll notice, as the cations on this side. Okay, so hydroxide and sulfur are insoluble with everything except calcium, strontium, and barium, and these up here. So there's 7 that each of these two are not soluble with. Carbonate and phosphate are insoluble with anything except these 4 up here. Okay, so just remember how to read this. So I'll do a couple of these and you do the rest of them. So it's silver, and this should be a small br. I never corrected that from the original assignment. So we'll write it like that. Silver bromide. Okay, so you come over here and there's silver and there's bromine. So this is going to be soluble with anything except these 3, and silver is one of those. So that's insoluble. Okay, strontium hydroxide. So hydroxide is insoluble with anything except these 3 and these 4, but strontium is one of these 3 down here, so that means these 2 are soluble together. Okay, so that's soluble, and you just have to write that like that. Okay, and you go ahead and do the other 3 based on that. Okay, so identify the principal quantum number and the subshell of each of the following elements. Okay, so I give you an example of carbon is in the 2p. So let's just review. Looking at the periodic table, right here, anything in these 2 columns is S. Also, you add helium. Helium is also an S subshell. So these 2 columns plus helium. P is this square right here. Those are all P subshells. Come to the transition metals, D. D is everything here. Those are D subshells. And if you come down below, these 2 are F subshells. Okay? Alright, so let's go ahead, and it's just identifying those is all you're being asked to do. So we start with carbon. So carbon is here. It's in the 2nd row, and it's in the P subshell. Alright? How about neon? Neon is in the 2nd row, and it's also in the P subshell. Okay. And I'll do one more. Copper. Copper is here, and it's in the 4th row, but it's in the 3D. Remember, the 3D is 1 row below its number. So it's actually in the 3, and this is the D subshell right there. So copper is 3D. All right, so you go ahead and do the last 2, potassium and neodymium. Okay, so what we're going to do now is draw the Aufbau structures and the condensed electron configuration here. So we're going to start with copper. Copper again is in the 3D right there. And so you've got to fill everything up to the 3D. And so we're going to start with the 1s. Okay, these should have S's behind them, so 1s. And then you got to fill the 1s before you go to the 2s. 2s, fill. Okay, now fill these in the correct order. Up, 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 down, down, down. Now that one's completely filled, so you say, what difference if I did it in the right order? If you don't practice doing it in the right order, you're going to get it wrong sometime when you don't have a filled subshell. Okay, next is 3s, and we're looking for 3d, so that's up and down. 3p, so again, we're just going like you're reading a book, okay? From left to right, top to bottom, across, across, across. We just did 3s, now we're going to do 3p. Okay, we're there. Now we're going to go down to the next, and that's going to be the 4s right there. And then we're going to do the 3d because that's where copper is. And it's 1, 2, 3, 4, 5, 6, 7, 8, 9th element over. So we got to count out 9. There's 9. Okay, so that's what it would look like. But we know that a subshell is more stable when it has either a filled or half filled, when it's either filled or half filled. So here, 4s is filled. That's very stable. Here 3d though is not either filled or half filled. So what the alpha is going to do, it's going to move this electron up here. So now the 4s is half filled, but that's still very stable, and the 3d is filled, and so that's what this would look like. Okay. So now what we're going to do is remember that a noble gas is any filled p subshell. So this one, the 1s is filled, and that's helium. The 2p is filled, that's neon. And the 3p is filled, that's argon. So this is argon, this is neon. And this one down here, it's the only one that's not a p, is helium. Okay? So that means we're going to come down here. We're going to start with argon right here. And then we're going to add a 4s1 and a 3d10. Okay, and that takes care of that. All right, now we're going to come down to titanium 3+. It's going to ionize. Okay, if you look at your charge number by ions sheet and you look at titanium, it can do a 3+ charge. So what we're going to do is just go ahead and draw titanium. Let's find it first. It is in the 3D subshell. Okay, it's right there. So let's go ahead and draw up to there. And it's the second element over in the 3D, so it's going to be like this and like this. So that would be titanium. Now it's going to ionize 3 electrons, okay? And remember, the 4s go before the 3d, okay? Just one of the quirks, one of the rules you got to memorize. So it's first, if it's going to lose 3 electrons, it's going to lose these 2 and then this one right here, okay? Does it matter which one of these you took out? No, these are called degenerate energy levels. You could take out either one, but it seems more logical to take out this one. So we're going to take that out, and we're going to take these 2 out. Okay, so what's the nearest noble gas? Right here, it's argon again. It's at the end of the 3p. So we're going to come down here. Be sure I'm on screen here. So argon and then 4s0. You actually can get away with not writing 4s anything because there's nothing there. But I like to do it this way and show that, hey, I know that there's nothing there. It's not a mistake. And then this one is 3d1. Okay, and that's how you would draw the alpha, condensed alpha for that. Okay, now we're on to problem 31. What does PES determine? It's photoelectron spectroscopy, and I'm just going to say it, you write it. It determines the ionization energies or binding energies, so they're both the same thing, of atoms of a particular element. Okay, so that's what it's telling you. All right, so let's go ahead and fill these in. So the highest number is on the left and the lowest is on the right. That means the highest ionization energies are going to be the ones closest to the nucleus. They are the hardest electrons to pull out. So this one must be the 1s, okay? So it's 1s, okay, right here. Here is 2s, And you can tell how many there are because 1, 2, each line represents 1 electron. Over here you have 2p, and we know the 2p holds 6 electrons. 1, 2, 3, 4, 5, 6. So this is 2p. Okay. Then we get over here, and here's 3s. Okay, and finally we get to the 3p, and we see the 3p only has 1 electron. Okay. So that tells us, I'll go ahead and just write a 1, although you don't have to do that. That tells us it's the first element in the 3p. Here's the 3p right here, and that would be aluminum, okay? So we've identified that as aluminum. Okay, and that's how you do that. Now, why are these things spread out? Because remember, there's 6 elements in the 2p as an example right here, and they don't all have exactly the same ionization energy, okay? It gets higher and higher as you go from left to right. So that's why there's a little space there. It just represents that difference between, in the case of 2p, in the case of boron versus neon, okay? All right, move on. Next problem. Okay, isotope mass use, fractional abundance. Again, that's the same thing as percentage. So what they want you to do is figure out if you have the masses and the percentages of isotopes, you get that from mass spectroscopy or spectrometry. So that's what this question's asking you. What does mass spectrometry determine? And a lot of you got that right on the last quiz. It determines the mass of each isotope of a particular element and what percentage of the isotopes are that mass. So mass and the mass and the percentage rather. Okay, so here we go. I'll do one with you here. So this one's going to be, first of all, you should know how to get a percentage into a decimal. You're going to move this decimal over 2 places, and so that's going to be 0.787. Okay, that's the percentage as decimal forms, 2 places over. Okay, times, and then there's the actual mass. All right, and you'll multiply those two together, you'll get a number right here, okay? Next, you're going to multiply this and 0.1013 right there times 24 right there, and you're going to get another number there. This is 25.983. This is going to be 0.1117 right there. You multiply those two, so I put a times sign, and then when you get these 3 numbers over here, you're going to add them together to get the atomic mass. That's the number that you would see on the periodic table. Okay? So I'll leave that for you to do the math on those. Okay, compute the atomic mass for chlorine. So you got to ask yourself if this is a percentage over here or a base peak. The way you tell is the highest line on a base peak will always be 100. Well, this highest line is not 100. It's something below 80, and you can estimate what that is. I think it's about 78. I think this one but they have to add up to 100. If it's not a base peak, they have to add up to 100. So if this is 78, then this is going to be 22%. Okay, so we're going to start with the 35 line. Okay, I'll just write that so we reference it. Okay, and that's going to have be 35 times 78%. Okay, for the 37 line, 37, and we're going to say if that's 78, then this has to be 22%. They have to add up to 100. Okay, so now you simply adjust the decimal just like we did up here. Move it over 2 spaces, 0.78, 0.22. Multiply them, come up with a number there, and add those 2 numbers, and you get the atomic mass. Okay, and you don't have to identify it. It already says it's chlorine. Okay, all right. So practice those, and be sure you know how to do those. Okay, this one is also a mass spectrometry, and it is a base peak. How do you know? Because the tallest line is 100. So these can't possibly be percentages because they'd have to add up to 100. This one's already 100. It just referenced 100 as the height of the highest one, and then everything else is set relative to 100 here, okay? So this just requires an extra step to do. So we'll start with I'm going to estimate how high I think each of these lines is. Again, it's not a percentage. I'm going to say this one is 10. I'm going to say this one is, I take that back. I'm going to say that one's 5. And if you got a different number than me, it's okay, as long as you know what you're doing. I'm going to say that's 5. I'm going to say this one is 10. I'm going to say this one is 20. I'm going to say this one is 80. 85, I'm going to say. It looks like it's lined up with that one right there. Let's see. No, I'm going to say it's a little higher. It's 90. Again, if you got 85, I don't care, as long as you understand. So I'm going to say this one's going to come over like this, and that's going to be 90. Okay, and then this one, of course, is 100. Okay, so your denominator is going to be all of these numbers added together. 100 plus 90 is 190, plus 20 is 210. Add 10 more is 220, and 5 is 225. Okay, so I get myself set up here. So I'm going to start with the 5 over here on the left, and then go down and do the 10. So this one is going to be 5 over the sum total at 225, and that's going to give me a percentage. Okay, and then it's times this number right here, 12. And you come up with a number there. Then you have 10, and 10 is also going to be over, they're all going to be over 225. That's when you added all 5 of these up. And you find it when you do all these fractions like this, you're going to end up adding up to 1, which is 100% in decimal form, okay? And then you're going to multiply that by 13. And you're going to get a number there, you're going to get a number there. This is 20 over 225. And that's the last one I'm going to do, okay? And that's going to be times 14, okay? And that's going to give you a number here. And then once you do all those 5 numbers there, you add them together and you get the atomic mass of this isotope. And you can identify it if possible. I remember this one was kind of funny. It didn't really end up at any particular element. But anyway, just do the numbers and you're good, okay? And understand why you're doing it. Okay, we are now... Okay, so here we go, and we're now on number 36, and now the next 3 problems are solution stoichiometry, okay? And let's actually answer this, and I didn't give it a number, so let me call it 35A. Okay, when you stir salt into water, what is the solute, the solvent, and the solution? So the solute is what's getting dissolved, that's the salt. The solvent is what does the dissolving, that's the water. And the solution is the 2 of them together, the solute and the solvent together. Okay, so you can write out that answer there. All right, now this is solution stoichiometry. It's my favorite stoichiometry problem because it ties a lot of things together. So solid seawater has a density of 1.27 grams per milliliter and is comprised mainly of sodium and chloride and water. What is the molarity of a solution of 5.72 mass percent sodium chloride? Okay, so you're going to go to your packet and turn to page 9, and these are all the definitions you need for solution stoichiometry. And the one that we do probably 90% of the time, 80 to 90%, is molarity. It's moles of the solute, sodium chloride, over liters of the solution, the 2 of them together, not liters of water. Be careful on that. Although they tend to be very close, okay, in terms of the volume. Okay, so here we go. So we're going to go ahead. It says, what is the molarity of a solution of 5.7 mass percent? So what we're looking for, and you do way over on the right because you're going to need a lot of space, and it's moles of NaCl over liters of solution. Okay. There you go. All right, so now we got to deal with the mass percent, and we are going to write our assumption that we always write with mass percent. Assume. So you assume that the solution, you went down to the ocean and you chose exactly 100 grams of solution. So that means that you're going to get, if you have 100 grams of solution, then 5.72 mass percent is going to give you 5.72 grams of NaCl. So we're going to just write that here. Okay, there's that right there. So that's what we're going to start with. We're going to start with that since that's what it told us we had. So we're going to come way over here. Okay, Good. All right. So now we have to build a bridge from here to here. So you treat it as a top story problem. So you need from grams of NaCl to moles of NaCl. And that should ring a bell. That's molar mass. Grams to moles, moles to grams is molar mass. So let's go ahead. I'll give you the molar mass of NaCl. I could ask you to do it, but let's just shorten it here. So it's 58.44 grams per mole. Okay. One more thing you can do is this. This is 2.27 grams per milliliter. What that means is you get, for the solution, it weighs or has a mass of 2.27 grams for every 1 milliliter of solution. So both of these are solution. Grams of solution, milliliters of solution. So I'm going to write it here as an equivalency. So there it is. That's how you would write this as an equivalency, okay? Now we have everything we need set up to get going. So we're going to start with grams to moles of NaCl, and we're going to use the molar mass of NaCl. So you don't have to draw boxes if you don't want. We need grams to disappear from the top and moles to appear. That means we need 1 mole NaCl to appear on the top. And 58.44 grams on the bottom. Grams of NaCl cancels and cancels, and the last man standing on the top is moles of NaCl. So you're done with the top. Now we go to the bottom, and we have grams of solution. We need to get to liters of solution, okay? So we need a relationship, because grams is an amount of mass, liters is an amount of volume, but we have that relationship. That's what density gives us. Okay, next thing we have to do is on the denominator, we're on the bottom story, grams of solution to liters of solution. So first we need to get from grams into milliliters. We have the density that does that. It relates the volume to the mass of the solution, the seawater. So we're going to go ahead and do this. Right there, grams of solution cancels with grams of solution. And now we have milliliters of solution. We need to get to liters of solution. So we use one of our 3 standard conversions, and that's 1,000 milliliters equals 1 liter. So we're going to do that, and we're going to put milliliters on top. And that's true for anything, but let's write what we're dealing with here, solution. Okay, and on the bottom, so we have milliliters of solution cancels and cancels, and the last man standing on the bottom is liters of solution. And if you do the math on that, there's the answer over there. So that's going to be 2.22 moles NaCl for every liter of solution. Okay, there it is, and you can just call that molar, 2.22 molar. Okay, that takes care of that problem. All right. Okay, I'm going to go ahead and end this video here, and I'm going to go to number 37 on the next video.